Hello and welcome everyone. Today we are going to give one example of the Beer-Lambert Law that we studied in the last class. One of the most important example of Beer-Lambert Law is the pulse oximeter that we are using in day-to-day life nowadays. So let us see this problem that you have in our hand right now. So what is given to us is that considering the extinction coefficient of oxygenated and deoxygenated hemoglobin. So both of these extinction coefficient of hemoglobin, deoxygenated and oxygenated hemoglobin as a function of wavelength has been mentioned over here in this graph. How it varies along the wavelength from around 250 nanometers to around 1000 nanometers. And what is asked is to use the Beer-Lambert law and to calculate the approximate concentration of oxygenated and deoxygenated hemoglobin, total hemoglobin and oxygen saturation, that is also known as SO2. Okay, so there are few assumptions. So assume that the pulse oximeter is working at 600 nanometers and 660 nanometers and 940 nanometers. Also few more assumptions have been given that the transmittance at 660 nanometers is around 93% and transmittance at 940 nanometers is around 86%. So these are the two things that are given to you. And one more thing, that is information that is given to you, that you can approximate the thickness of your finger to be around 1.5 centimeter. Okay. So let us try to see this example. Let us try to solve this example. Okay. So what is given to you? So what is given to you is this finger, for example, over here, and there are two LEDs. One is operating at 660 nanometers and another is operating at around 900 and let me just check again what was the 940. Okay, 940 nanometers. Okay, so these are the two different wavelengths of the two different LEDs, and then you have a detector over here in the bottom. So this is the detector. Okay, and this detector, the thickness of this finger is to be assumed as around 1.5 centimeter. Okay, so the light actually propagates through this and then interacts with the detector. So this is the source in the top. In the bottom we have the detector. Okay. So now in our earlier class we learned about the transmittance. The transmittance is given by the following equation. So if you see the transmittance, it is actually given as exponential of minus mu a into h, where mu a is nothing but absorption coefficient and h is the thickness of the medium where the light is propagating. And then we so this is as a function of the spatial, how the spatially it is varying. And there is one more equation that we derived, and that was exponential, which is based on the concentration, that is exponential of minus epsilon C h. Here epsilon is nothing but the extinction coefficient, or the the one that was given in the graph, molar extinction coefficient. C is the concentration of the species, and h is again the thickness of your sample or medium where the light is kind of propagating. So what we can do from these two equations is that we can try to combine them. Okay, okay. Just let me check if this is the correct equation. Oh, sorry, this is so it has to be 10 power epsilon. It's not E, but it's 10 power epsilon. Yeah, it's 10 power of minus epsilon CH. Okay. Now let us try to combine this equation. How do I combine it? I just write it down as minus mu a into h equal to 10 power minus epsilon CH. Okay. Now I can just take this logarithm over to the right hand side. So what I can write it as minus mu a this has to be like okay, let me just write it again. It has to be like exponential minus mu a h. Okay, now I can write as logarithmic. I can just take it on the other side. So I write ln of 10, and then I can just write epsilon c h. Okay, so I can take the top part and move it towards the left hand side. So I can write mu a h equal to minus epsilon c h into ln of 10. Okay, so this is what I come towards for a single species. Okay, what I'm doing right now is for a single species. It's not for dual species or 3 species or 4 species, just for single species operating at a particular wavelength. So I can just remove the h over here. I can just write the equation of mu a, that is nothing but so my negative sign also goes away. So I have something like epsilon c ln of 10. Okay, so this is for a particular wavelength. Now what are the function of wavelength? So if I want to write as a function of wavelength, so it would be mu a is a function of wavelength, that is absorption coefficient is a function of wavelength. Epsilon, molar extinction coefficient, is again function of wavelength. Concentration is not a function of wavelength, it's what kind of it's already flowing within the sample. And then ln of 10 is nothing but the scalar value, right. Now what we need to do is that what we are given is there are 2 constituents, okay. So that we want to find the composition of or the concentration of, right. So now to get 2 of this composition, we need to have 2 different equations. How do we have 2 different equations? Is that we shine the light of 2 different wavelengths, right. So we can write the equation of for 2 different wavelengths for 2 different compositions or 2 different constituents, okay. That would be mu a of lambda 1, which is equal to epsilon of your first species. For example, it would be HbO2, and this would be of lambda 1 into concentration of Hb, this is again HbO2 into ln of 10, okay. So this is my first equation, okay. My second equation would be for when I am operating at lambda 2, that is mu a of lambda 2 is equal to okay. So one thing that I would also be writing that is would be not just this equation, but it has to also be adding with the extinction coefficient of Hb of lambda 1 concentration of Hb into ln of 10. So this whole combination is my equation 1, okay. Now I am operating at lambda 2, and that I can write is now mu a of lambda 2 is equal to again I write epsilon of HbO2, but now I am operating at lambda 2, that is around 940 nanometers. So I write lambda 2 over here instead of lambda 1, C of HbO2 concentration of oxygenated hemoglobin and logarithmic of ln 10 plus extinction coefficient of Hb at lambda 2, that is 940 nanometers, concentration of Hb into ln of 10. Okay, this becomes my second equation. Now if you see this carefully, let us try to see what information do we already have. Okay, now we know the equation that we already know, that transmittance equal to exponential minus mu a into h. Okay. Now we already know what is the value of h. Okay, we already know what is the transmittance. It's already given in the problem in our hand, right? So we can actually find mu a. Okay, so mu a is kind of we can actually find it out, right? So we already know what is mu a for 2 different wavelengths. We already know it now. Epsilon of or extinction coefficient of oxygenated hemoglobin at lambda 1, we can find it out from the graph that was mentioned in that question. Okay. Similar to this, we can also find extinction coefficient of deoxygenated hemoglobin at lambda 1, and similarly of at lambda 2 as well, right, at 660 nanometers and at 940 nanometers, both the wavelengths we can find what is the extinction coefficient. This is just a scalar value, so we definitely know this. Okay, what we don't know is the concentration of hemoglobin oxygenated and deoxygenated. So these are the two things that we don't know. Okay, so now we have classical case of two equations and two unknown, and we solve this to find what is the what is this concentration. Okay, and from this we can also calculate what is the oxygen saturation. Okay, so now let us find it out. Okay, so now what is given to us is that the transmittance at 660 nanometers is given as 93%. Okay, that means that your transmittance at the is nothing but equal to 0.93. Now what is this 0.93? That is equal to exponential of minus mu a into h, right. So now what is epsilon of minus mu a into 1.5 centimeters. Now this is in centimeters because the molar extinction coefficient also was in order of centimeters, right, inverse of a centimeters perhaps. So if it would have been in meters or in mm, so you have to be very careful what is the units of the length that is given in this in these problems. Okay, so I just write ln of 0.93 is just equal to minus mu a into 1.5 centimeters. So I just solve this and I actually get this, that mu a is approximately equal to 0.048 centimeter inverse. Okay. Similarly, I know the transmittance of 940 nanometers is around 86%. Okay. So again I can use this equation of 0.86 equal to epsilon of mu a into h, where h equal to 1.5 centimeter. So I just solve this equation again, ln of 0.86 equal to exponential minus mu a at 1.5 centimeters. So I just solve this and I found that mu a, okay, this is at 940 nanometers is around 0.10 centimeter inverse again. Okay, so this was of 660 nanometers. Okay, so these are the two main important things that we get now, mu a, value of mu a. Okay, and now we are going to use this value of mu a over here. Okay, at lambda 1 and at lambda 2. So now let us substitute all the values together into our equation 1 and equation 2 and try to figure out the two equations that we need to find for. Okay. So what do we have now? We have the two equations, we just need to substitute the values. Now one thing that we need to know is from epsilon of HbO2 at lambda 1 and epsilon of Hb at lambda 1, that is at 660 nanometers. So here lambda 1 is nothing but 660 nanometers, okay, and lambda 2 is 940 nanometers. Okay. Now you can just see this thing from this graph. Okay, the graph that is mentioned over here, you can see over here. So at 660 nanometers you can just try to see, and at 940 nanometers you can just try to see. Just draw a line at 660 nanometers and write and just try to figure out what is the value of molar extinction coefficient, that is centimeter inverse over molar. So 1 over centimeter molar, right. So if you draw a line and just find whatever is the value of epsilon for these two wavelengths, you will find that the value of epsilon of HbO2 at 660 nanometers, sorry, epsilon of Hb at 660 nanometers. So we need to find this from the graph, epsilon of HbO2 again at 940 nanometers and epsilon of Hb at 940 nanometers. Okay, so what are these values? So if you just draw a line, and if you draw a line, you will actually get it. So this is nothing but equal to 300. Now this is centimeter inverse per molar. So it is the same thing for all of them. And this is around 1000. Sorry, this is around 4000. Okay, and for 940 nanometers, this is around 1000, and then the Hb at 940 nanometers is around 700. Okay, the units are the same. So this actually is coming from the graph. The graph which is epsilon versus lambda value. Okay. Now you know these values, right? So now you again go back to our equation now. Now you know these values that you know these values now, all these values. Now you just need to substitute all of them and try to find out your concentration of HbO2 and concentration of Hb. So let us now put this into the equation of equation 1 and 2. Okay, and try to find out what is the values. Okay, so what you get is the following values of concentration of oxygenated and deoxygenated hemoglobin. So now we know these equations and we put it. So we know the equation is like 0.048. That is for the first equation I am just writing. That is inverse centimeter inverse is equal to you have 300. That is the value of epsilon, and you write into 2.3. This 2.3 is nothing but ln of 10, and I write concentration of HbO2. Okay, plus I need to write it as 4000 into 2.3 into concentration of Hb. Okay, similarly for the second equation, so this is my first equation and this is my second equation now. Second equation is nothing but 0.10 centimeter inverse is nothing but equal to 1000 into 2.3 concentration of HbO2 plus 700 into 2.3 into concentration of Hb. Okay, so now as you can see, now there are two equations and there are two unknowns. The two unknowns are the concentration of HbO2 and concentration of Hb. Okay, so I just need to put in things into perspective now. That is, I can put this 2 by 3 on the left hand side, and what I get is something following, and I put CHbO2 for simplicity I put it as A, and concentration of Hb I put it as B. Okay, so for simplicity I can just put this, and what I get is again two equations. It's 0.02 is nothing but equal to 300 A plus 4000 B, and then I get 0.043 is equal to 1000 A plus 400, sorry, not 700, this would be 700, correct, B. Okay. Okay, now I just need to substitute one into each other. So what I can write is that I can just solve these two equations. Now it's kind of very simple to solve these two equations. You just need to multiply, either you can multiply or put A into function of B and then substitute in that B, and you find A and B. So if you find this, if you go ahead and solve these two equations, you will find that A is nothing but 0.02 minus 4000 B divided by 300. Okay, now you put this A into this and you can find B. Okay, so if you do that, you will find that B is equal to 0.13 times 10 power minus 5. and once you find B, you can put B into this equation and you will find what is the value of A. So you find that A is nothing but, so this is actually molars, and this A is nothing but 4.9 times 10 power minus 5 molars. Okay. So what the concentration of HbO2 is nothing but 4.9 times 10 power minus 5 molars, and concentration of Hb is also given something like this, is actually equal to 0.13 times 10 power minus 5 molars. Okay. So now if you want to find the total hemoglobin, so it's HbT is actually the concentration of both Hb plus HbO2. If you add both of them, so you will find that it is around 5.03 times 10 power minus 5 molars. Okay. And now if you want to find oxygen saturation, is also given by SO2. It's actually nothing but concentration of HbO2 over total concentration of hemoglobin. Okay. So if you just substitute the values of both of them, that is 4.9 times 10 power minus 5 divided by 5.03 times 10 power minus 5 molars, you will get that it's around 0.97, nothing but approximately 97%. Okay. So you can find your SO2 to be equal to around 97%. So this is kind of for the healthy patients, right? So this is what you actually see in your pulse oximeter, SO2, that is oxygen saturation. That actually this is what actually happens inside the pulse oximeter to find the value of 97%, for example, for a healthy patient. Okay. Okay. Thank you.